All right. So we have Dr. Richard Cartwright from the Johns Hopkins Applied Physics Lab presenting on our Uranus's large moons ocean worlds, the developing spectroscopic picture. Go ahead and take it away.
Thanks, Mallory. Okay, so today is going to be a bit of an overview of the ground-based observations we've been making for the past 12 years or so, incorporating also older data that was collected by Andy Rivkin and Will Grundy back in the early 2000s, and then some more recent data that we've collected both from the ground and more excitingly using the near-spec spectrograph on James Webb. So I'll show some of those results as well. And most of the work that I have been involved with has been thinking about how exogenic processes change the surface compositions of the Uranian satellites. And I'll recap this stuff as we go along, primarily thinking about how charged particles have changed their surface compositions, as well as the accumulation of dust originating from retrograde irregular satellites. But as time has gone on, there is this endogenic component to the surface compositions of the Uranian moons that's started to loom larger and larger, and the JWST results certainly drive this home as well. Now, most of this talk is going to focus on the four largest moons. I'm not going to say that much about Miranda. I'm sorry for those of you who are large Miranda enthusiasts. A lot of good work has been done on Miranda recently by Riley DeColobus, and so I suggest you check out those papers, and I'll reference them at some point on one of the slides. And even though I'm going to talk about the four largest moons, we're really going to spend most of this talk thinking about Ariel. Okay. So to begin with, I'm going to have a few slides that kind of summarize what we know about the Uranian moons from a bulk compositional perspective and what might be happening in their interiors from a heating perspective. But this is going to be super overview. It's not, we're not going to dive into this in any stretch. And I don't even know if I know enough to be dangerous in these particular topics. I just know little bits. And to start with, there are three broad formation scenarios for how Uranus's five large moons, the classical moons, may have come about. Perhaps they formed in the Uranian subnebula, in which case their bulk compositions might be somewhat solar-like and they would be ancient. Alternatively, perhaps the Uranian moons formed after a giant impact, which tilted Uranus on its side. And in this scenario, it's possible that the moons incorporated a large amount of the impactor itself, which may have originated in the outer solar system. And so they could be enriched in carbonaceous chondritic material and perhaps other components you would expect to find in devolatilized comets. Or alternatively, perhaps they formed from a massive debris disk that used to orbit Uranus. So you can think of this essentially as a icy satellite production conveyor belt with icy moons popping out and then migrating to their current orbits. And in this scenario, the moons would be possibly younger than the age of the solar system or the age of the Uranian system, and also could be more enriched in organics compared to the other formation scenarios. Now, after forming, the Uranian moons most likely went through resonances, which they orbital resonances, which they don't currently possess anymore. And these resonances could have spurred significant tidal heating and melting of their interiors and then subsequent resurfacing. This is a popular or an important paleoresonance or fossil resonance is the 5.3 mmR that was shared by Ariel and Umbriel, which may have occurred maybe 500 million to 1 billion years ago, spurring significant heating of Ariel and driving some of the resurfacing that we see today, which I'll show on a subsequent slide. An interesting wrinkle in all of this, there are some models that suggest that along with these mean motion resonances, the five classical satellites might actually have some sort of coupled resonance that they all share. And in this scenario, when two moons like Ariel and Umbriel go through a resonance, the other moons may experience tidal heating as a result as well. This heating would be minor in Titania or Oberon, but poor little Miranda would get beaten up pretty badly by this. And so it may have been heated extensively, even if it wasn't explicitly in a resonance with other moons. And this could help explain why Miranda seems to have gone through periods of rapid or of rampant resurfacing that then seems to get shut off and then starts again later on. So then thinking about their interior, some recent modeling work led by Julie Castillo showed that the moons, at least the four largest moons, not Miranda, unfortunately, could have residual oceans. And these could be 10 to 20 kilometers in thickness. They would be hypersaline and maybe, I believe, less than 270 Kelvin, right? It says there on the slide. And they are unlikely to be connected to the surfaces of these moons by any sort of geologic conduit, at least in this residual ocean scenario. To some extent, I kind of see this almost as a worst case scenario for aerial. I still think there's possibilities for geologic connectivity, but that's speculation, and I will continue to speculate about that throughout this talk. Okay, so then getting to the moons themselves. The 5 large moons were observed or imaged by Voyager 2 during its brief flyby in 1986. We only saw the southern hemispheres of these moons by and large. We got fairly close to Miranda and Ariel, achieving 250 meters per pixel and a kilometer per pixel, respectively. And that was fortunate because these moons have some pretty wild surface features. Miranda's surface, at least its southern hemisphere, is dominated by these 3 large coronae, which are polygonally shaped regions of intense deformation and have been tectonically modified extensively, and perhaps there's a cryovolcanic component embedded in there as well, and they may have formed from ascending diapirs. The 3 coronae that we see are almost certainly formed at different times based on crater counting, age estimates. And so this goes back to the point I was making previously that it looks like Miranda has undergone multiple periods of resurfacing that shut off and then get started again. On Ariel, we see lots of evidence for resurfacing, but it's a totally different style than Miranda. Again, we see lots of evidence for ubiquitous tectonism and also some tantalizing hints for cryovolcanism. That yellow box, the arrow is pointing to what was labeled a medial groove, which exhibits double ridge topography. So it's 2 flanking ridges with a topographic depression in between. And this is reminiscent of some volcanic features on Earth, and perhaps this is a conduit to Ariel's interior, which may be active still, or perhaps is no longer active and was previously. So for the 3 outer moons, the data that we have are much worse, and from a spatial resolution perspective, these moons are darker, especially Umbriel, and they are older than Ariel or Miranda, but we still see some pretty interesting geologic features, including this bright annulus in that blue box around on the crater floor of Wunder Crater, which is located near the center of Umbriel's trailing hemisphere. This could be a cold trap for CO2 ice and other volatiles, so CO2 molecules generated elsewhere that then end up forming a large cold trap, or it could be a post-impact cryovolcanic infill of salts and volatiles as well, and that might explain why it's bright. On Titania, we see a large hemispherical chasmata, or equatorial chasmata, formed from tectonism. There could be some smoother regions on Titania too that have been speculated to be associated with cryovolcanism, but there's not too much to back that up at the moment. And then Oberon, the data are quite poor. We see some dark crater floor deposits, which look quote unquote smooth, but that's smooth at 6 kilometers per pixel. Again, it's been speculated they could be related to cryovolcanism, post-impact cryovolcanism, but again, who knows, especially at 6 kilometers per pixel. Okay, so that's a whirlwind tour of what's going on with the moons in terms of their interiors and surfaces from a geologic perspective. Now I'm going to focus on the work that I do using ground and space-based telescopes to characterize the surface compositions of icy bodies and ocean worlds. And for this particular talk, focusing on the Uranian moons. And we're really going to focus mostly on the near infrared, so data collected primarily with specs on the IRTF on Mauna Kea, and then in more recent times over the last year, near spec on JWST. So this is a busy slide what you're looking at are grand average IRTF spectra for the for the five largest moons, including Miranda, between about 0.9 to 2.5 microns in blue and orange for the leading and trailing hemispheres, respectively. And I'm going to talk about specific spectral features on subsequent slides. This is just an overview of some of the data that we have. You can see that for Miranda, the error bars are quite chunky. It is the faintest of the moons. And again, it wasn't a large focus of some of the early work that I did looking at the moons. And Riley DeCalabos, again, those papers from 22 and 23, has published much better data, including all the IRTF data are also in those papers as well. So if you're interested in spectral properties of Miranda, I would check those out. Now, they're beyond the logistical reasons that we're not focusing too much on Miranda in this discussion. The spectral properties of Miranda at first glance seem similar to the other Uranian moons in terms of having broad 1.5 and 1.6 micron features, as well as characteristic 1.65 micron features associated with crystalline water ice. But there are subtle differences between Miranda and the other moons that we'll get into. Also for Ariel, Titania, and Oberon, we did collect data between 3 and 4 microns with IRTF. Those colored error bars that you see over those wavelengths are binned, I think, to a spectral resolution of about 50. The gray bars in the background are the actual native data. So we're talking about extremely low signal at these wavelengths. It's really hard to observe icy objects over longer wavelengths. They're just dark because water ice absorbs so strongly. And Earth's atmosphere is busy trying to gobble up all your photons as well. And beyond 4 microns, things get even worse. And we'll come back to that. So what does all this data tell us? What's going on here? So building on previous work that was published in 2003 and 2006 by Will Grundy and colleagues, we looked at the distribution of these different surface constituents on the Uranian moons, keeping in mind that all these data are disk integrated. So when we talk about distribution, we're really talking about leading versus trailing hemispheres for these tidally locked objects. So I'm going to start with the plot on the right, grand average spectra for Ariel and Titania, and we'll start with Titania. There's no vertical offset here between those two spectra. And so you can see there's a slight difference in reddening between Titania's leading and trailing hemisphere, and the water ice features are slightly stronger on its leading hemisphere as well. And then going up now to Ariel, and those are vertically offset for clarity. We see these narrow CO2 ice bands dangling off the base of the 2-micron water ice band, and that green spectrum right at the bottom is of a laboratory spectrum of pure crystalline CO2 ice, showing that the spectral properties for CO2 on the Uranian moons are remarkably similar to what we've measured in the laboratory for crystalline CO2, which is unusual. Most of the CO2 we see on icy satellites, for example, at Jupiter, don't exhibit these features. They don't have crystalline ice on their surfaces. Okay, so what might be happening? So now going to the plot on the left here, what we think is happening, we see more CO2 on the trailing hemispheres of these satellites, in particular on Ariel. We don't see any CO2 on Miranda, which is part of the reason why it's not a big part of this talk. It doesn't have any CO2, at least none that we've detected to this point. And then along with the CO2 on the trailing side, we have stronger water ice bands and more red material on the leading side. And so we think this is being driven by exogenic processes primarily, with dust impacts primarily from the retrograde irregular satellites colliding with these moons, overturning regolith, exposing fresher water ice, and delivering red material, with this trend being more important on the outer moons. And so that might be why they are redder compared to the inner moons. So Titania and Oberon being redder. And I'll show this on a later slide. And then the CO2 ice on the trailing hemispheres, it's the preferred hypothesis, the prevailing hypothesis is that that's formed from radiolysis of charged particles bombarding their surfaces, interacting with carbonaceous material mixed with water ice, generating CO2 molecules. Although we'll see these hypotheses are going to get more muddied as we go. So this is a plot showing the mean CO2 ice band areas for these 4 satellites. So you can see there's clearly a lot of CO2 on the trailing hemisphere of Ariel, And then there's a marked drop off for the other three moons, and then a slight drop as you go away from Uranus with increasing orbital distance. These data hint that there may be a little bit of CO2 ice on the leading hemispheres of these satellites, but the detection is ambiguous in these data. But we'll see with JWST that CO2 ice is absolutely on their leading hemispheres, just to a lesser extent. Something else that I neglected to mention, so I'll go back here really quick. Those CO2 ice features we see on aerial are something like a factor of 1,000 weaker than the asymmetric stretch fundamental between 4.2 and 4.3 microns. Most of the time we detect CO2 on other icy bodies, it's between 4.2 and 4.3 microns with spacecraft data or space telescopes, because we can't see that feature from the ground, because CO2 gas in our atmosphere absorbs really strongly there as well, along with other gases. And so JWST was the first facility that was able to look at the Uranian moons of those longer wavelengths and look at the asymmetric stretch fundamental at 4.25 to 4.3 microns. And so that's just a little bit of pre-hype for what I'm going to show in a bit. Okay. So now, before going a little bit further, just to refresh everyone about the seasons of Uranus, it's tilted on its side. And so, and so, and so it's important to think about what this might mean, where the subsolar point migrates between 82 degrees south to 82 degrees north. And so there's quite a large seasonal variation in heating. The winter hemispheres of the moons get plunged into darkness and may reach an estimated 20 to 30 Kelvin. So really cold stuff is going to condense. Volatile ice caps are going to form. Whereas during summer and spring, the peak temperatures are between 80 and 90 Kelvin, at least in the regolith. And at these sorts of temperatures, CO2 ice is mobile. And so we would expect CO2 to migrate across their surfaces over seasonal timescales. So to investigate that idea, we compared the distribution of CO2 at low latitudes compared to high latitudes. And what we did see is a subtle but noted drop in the strength of CO2 ice bands on aerial with increasing sub-observer latitude. Now, again, these are disk integrated data sets, which is important to reiterate. So they're not spatially resolved. And so even though the subsolar point is increasing and moving toward the North Pole of aerial and the other Uranian moons, we're still getting some signature from the equator, from low latitudes in our data. Nonetheless, summarized here, comparing the gold data points to the blue data points, there is a drop-off in the amount of CO2 on aerial as we start to look at higher sub-observer latitude data sets compared to low latitude data sets. And so what we think is going on here, what the models suggest is as CO2 migrates, if you integrate this process over many seasons, the net effect is to concentrate CO2 at low latitudes due to diurnal variations in heating, making CO2 more stable there. Or in other words, during summer, the pole is just continually exposed to sunlight, and CO2 and other volatiles just get denuded and get stripped off and then migrate to cold traps. And eventually you integrate long enough and that ends up being at low latitudes. Okay, so this raises an interesting question. If CO2 is migrating, are the exospheres seasonal or are they persistent? And so as the winter hemispheres of these moons get exposed to sunlight in spring and they start to warm up, CO2 and other volatiles are going to sublimate, go into the exosphere and puff it up. But does this process only last maybe a couple of years or so and then the exosphere dies down? Or does the exosphere oscillate somewhat, but is it persistently there and persistently detectable? We don't have an answer to this question yet, but I think it's an interesting wrinkle in terms of trying to understand what's happening on these moons and whether, and the extent of CO2 migration. Is it purely happening at equinox or is it happening all the time? I suspect it's all the time, but we will find out. So now switching gears from CO2 to talk about the dust I was alluding to previously with coming from the irregular satellites. The modeling work suggests that dust grains from retrograde irregular satellites around Uranus migrates inward on slowly decaying orbits due to pointing Robinson drag. And most of that dust ends up coating the leading hemispheres of Titania and Oberon, which seems to be consistent with the trends in spectral reddening measured using Voyager 2 data sets, as well as data collected since then with ground-based telescopes. And so in the Uranian system, there could be a similar relationship between the irregular satellites and the classical moons collecting dust to that of Iapetus and Phoebe at Saturn. Of course, Iapetus's global or its hemispherical dichotomy in albedo is much more pronounced than anything we see at Uranus, but the process could be somewhat similar. Okay, this is a complicated plot or slide, sorry about that. But what I'm showing here on the left are vis polarimetric work, showing that the Uranian moons have much steeper negative polarization branches compared to both bright and dark icy moons at Saturn and Uranus. Though the authors of this work suggest this could be because the Uranian moons have crumbly and very porous regoliths, promoting a lot of scattering. And then in the middle there, that plot is IRTF spectra that we modeled, and that we found small grains are needed in order to fit the peak of the volume scattering feature there, the 3.6 micron water ice feature, between 1 and 2 microns in particular, that diameter of grains. And again, this is consistent with highly porous, highly scattering regoliths. And so what might be going on here is that the accumulation of dust on these moons, along with migrating CO2 that sublimates and then recondenses somewhere else, that these processes might help to build up a kind of puffy regolith that promotes scattering. Now, something else I forgot to mention, and I'll go back and just say it really quick, is although CO2 does migrate across these moons, it should gradually leave the system due to genes escape as well. And so CO2 has to be actively replenished. Again, the prevailing hypothesis is that is through radiolysis, continually making new CO2 molecules, but it's also possible CO2 is leaking out of the interiors of these satellites, as we'll talk more about. All right, so switching gears to talk about endogenic processes. Some of the best evidence in the ground-based data for this comes from a weak 2.2 micron absorption feature that's seen on all 5 moons, including on Miranda. And this feature in the Pluto system on Charon, Nix, Hydra, and Pluto itself is generally attributed to ammonia or ammonium-bearing compounds, which is interesting because ammonia hydrates, ammonia ice, etc., are pretty volatile in charged particle environments. It was estimated that ammonia exposed on the surface of Miranda, for example, might be completely removed in only 100,000 years. And so the presence of ammonia could be a spectral tracer for recent exposure of subsurface material, whether that's in craters, tectonic features, etc. This argument, this idea, kind of holds together pretty well for Miranda and Ariel because they have fairly young surfaces, but it completely falls apart on Umbriel, which has one of the oldest surfaces in the solar system. Its surface is comparable to Callisto, although with much chunkier error bars in terms of its age estimate, but still it's ancient. It doesn't show much evidence for endogenic activity anywhere on its surface, yet it has a prominent 2.2 micron feature. And so it's possible that more refractory components are contributing to this feature in the Uranian system, whether that's carbonates or phyllosilicates, or perhaps even just long-chain refractory organic residues. Now, in any of these cases, especially for the ammonia stuff, the phyllosilicates, and the carbonates, it's likely that they would have formed in the interiors of these satellites and then got expressed to the surface. So even in the scenario where the material is more refractory, I still expect it to be an endogenic, a natively derived component, as opposed to being generated on the surface from radiolysis or delivered in dust, etc. On the right there, these maps show the data points where we detect that 2.2 micron feature on Ariel and Umbriel, with the blue and red being the positive detections and the black being the negative detections. So you can see these data are intermingled. And so it's a maddening signal to try and pin down because we can't get a consistent lock on it. It doesn't display any sort of leading trailing asymmetry like the other components on these moons. So it could be that it's related to localized geologic features that we just can't see in the disk integrated data, which might help explain why the feature seems to be there sometimes, but not there all the times in the data that we're collecting. All right, so now switching to talk about JWST, which is observed the Uranian system a few different times over the past couple of years in a few different programs. The program that I led collected data last year, actually about a year ago, almost exactly. On the left there, that is a raw image cube of a slice at, I think, at about 3.6 microns of Ariel. and it's not spatially resolved in any of the data. Again, even with JWST, the Uranian moons are disk integrated. So here are the grand average spectra for aerial again, but now we're kind of zoomed in. And then some of the features I've been talking about: CO2 ice, ammonia, perhaps salts at 2.2 microns, and then the broad 1.5 and 2 micron water ice bands, all that stuff that we've been talking about. The longer wavelength data with the IRTF, no evidence for a water ice Fresnel peak, which is almost certainly there. It's just the signal is so low, we can't even see it in these data. And those black data points are the highly smoothed data that is represented by the gray stuff in the background. And then what did an hour of exposure time with JWST show us over this wavelength range? Just absolutely phenomenal data from a signal to noise perspective. Obviously, clear evidence for water ice, crystalline ice, the 3.1 micron Fresnel peak is certainly there, as well as something tantalizing happening around 4 microns, which I think could be related to a broad carbonate feature, which I'll touch on later. And then the real power of JWST, what's going on between 4 and 5 microns. Again, reiterating that the CO2 ice asymmetric stretch fundamental around 4.2 microns absorbs extremely strongly. And so I expected to see a really saturated CO2 ice band based on the presence of the shorter wavelength CO2 features. So of course, instead we see a peak, which was completely unexpected. So I'm going to zoom in here and showing the leading hemisphere as well, resoundingly confirming leading trailing asymmetries in water ice, CO2, and other things on these moons, here typified using aerial. We see clear evidence for carbon monoxide ice, which I'm going to dive into. At longer wavelengths, that whopping band of 4.9 microns is most likely a CO2 ice band, a biphonon plus phonon combination mode. So it's not the normal sort of stretching mode we're used to thinking about with vibrational spectroscopy. It's formed from collective oscillations across a crystalline lattice, or in other words, there has to be a good bit of CO2 there in order to start to see those features. And we'll come back to that in a little bit. Plenty of other stuff going on in these data. I don't have time to unpack all of it, unfortunately. All right, so comparing the aerial data to a few different models generated using radiative transfer techniques, different sets of optical constants, so generated by different folks in different labs at different times. Models 1, 2, and 3 are all pure CO2 ice. Model 4 is CO ice. So we confirm the presence of CO ice, possibly the heavy isotopolog 13 CO, which I'll show in a little bit. And then it's the modeling work we've done so far is able to somewhat approximate the scattering peaks using optical constants collected by the Cosmic Ice Laboratory, suggesting that there could be a layer of large CO2 ice grains on the Uranian moons causing these scattering peaks, which are most pronounced on aerial. The other moons don't show a peak, a double peaked low or double lobed peak like this. This is really just all about aerial. And then models 1 and 2, they don't do a good job in the asymmetric stretch mode wavelength range between 4.1 and 4.5-ish microns. But they do show other subtle features, including the 4.9 band I was talking about before, and this 3.33 band, indicating that there are subtle CO2 ice features on aerial as well, consistent with pure CO2 ice, which is what the ground-based data was telling us. And then here, just really getting into the weeds, this is the complex indices of refraction for CO2 ice from the Cosmic Ice Laboratory, the N and K values, compared to arbitrarily scaled aerial spectra, just to demonstrate that where N goes below 1 and K goes above 1 and really ramps up, we get that second lobe of the CO2 ice peak. And we think that this is representative of the largest CO2 ice Fresnel peak yet observed in the solar system. All right, so now going to carbon monoxide ice, which we had thought was on aerial. We kind of had hints about it in the ground-based data on aerial, but they weren't strong hints. But this resoundingly confirms that carbon monoxide ice is present, and CO2 is certainly unstable on the Uranian moons, and carbon monoxide is hyper volatile. It shouldn't be there. It has to be actively generated through one mechanism or another. As I said previously, we think we detected 13CO as well. That could be related to a nitrile band like HCN ice. I think 13CO is more likely, but we can't rule out other possibilities. And then taking a closer look at the 12CO feature at 4.67-ish microns, comparing it to lab data, it's not similar to pure CO ice at all. And in fact, seems to be most similar to CO ice mixed with CO2 ice, at least based on the presence of the short wavelength sideband to the carbon monoxide feature. We did also compare it to CO generated in CO2 ice substrates. So where you irradiate CO2 ice and you make CO molecules. And the resulting CO feature, which is shown in that bottom plot in blue and orange, is still offset and doesn't have the same morphology to Ariel's feature. So we're not confident that the CO on Ariel is exclusively generated from radiolysis. At least I think there could be a native component as well. And along with that, there's this longer wavelength sideband that we can't easily explain, but it could be related to CO mixed with water ice, as some lab data to show it, that a feature will show up here, or it could even be CO clathrates, so where CO is trapped in as a guest molecule in a crystalline lattice, probably of water ice. If it is clathrate, then that would be pretty good evidence that it originated in the interiors of Ariel and the other moons, because making clathrates on the surfaces of icy satellites is pretty hard. Okay, switching here to go back to just talking about CO2 ice and looking at the photon penetration depth, the folding approximation of photon penetration depths for different species compared to water. So the key here in that black oval, this is the asymmetric stretch fundamental mode wavelength range for CO2 and CO. And the take home is that 12 CO2, 13 CO2, 12 CO, 13 CO, if it's well mixed with water, you're still going to see those components at these wavelengths. Those spectral features should still pop out. But the thing that's interesting is we see these subtle features on Ariel that are outside of the asymmetric stretch fundamental wavelength zone. And these are consistent with concentrated CO2 deposits that are separated from water and other strong absorbers. They could be mixed with some CO, sure, and other carbon oxides, but that might be the extent of it. Furthermore, some of the features we see are really subtle on Ariel, and they suggest that there's enough CO2 that the photons have to penetrate through a fairly thick layer of CO2, perhaps on order of a centimeter. I know the geologists listening to this might say, who cares? But from a spectroscopist standpoint, a layer that's a centimeter thick is really kind of cooking with gas. Okay, switching from carbon oxides now to talk about hydrogen peroxide. We did look for this. This is a very important molecule on Europa and Ganymede, also suspected on Enceladus as well as Charon, generated from irradiation of water ice. And it can be enhanced. Some laboratory experiments, it's enhanced when the water is mixed with a little bit of CO2. So on the Uranian moons, we got water, we got CO2, it's in a magnetosphere. Seems like a good environment to make H2O2, but we didn't detect it at all. And the data have really high signal to noise. We don't see it on any of the moons. Maybe some subtle hints at 3.545 and 3.6, as I'm showing there, that could be related to formaldehyde, but that's speculative and certainly not related to H2O2. So what might be happening is that charged particles are unable to get to the water ice below the CO2, and the CO2 is hogging all the charged particles. That could be the case. Or, as has been speculated about or suggested based on the data collected by Voyager 2, and also some recent modeling work that's underway currently, perhaps the irradiation environment at Uranus is actually pretty quiescent. And in this scenario, the CO2 and other components are more likely to be endogenically derived and perhaps only enhanced by radiolysis, as opposed to being exclusively or primarily made through radiolysis. So some exciting work is happening here on the modeling front that I can only kind of poke at and speculate about, but I hope the papers will come out soon that will help elucidate what's going on with the Uranian magnetosphere and its interactions with Ariel and the other moons. Okay, so as I've been hinting at and getting at, are these volatiles that we see on the surfaces of these satellites, are they coming from the interiors of these moons, especially on Ariel, that shows these tantalizing geologic features that could be geologic conduits, along with the available modeling work that's been done to suggest that Ariel has experienced some heating in the past, and we see clear evidence for recent resurfacing. And so it's certainly possible that the CO2 and the CO, as well as the possibility for carbonates, are coming from the interior of Ariel and get expressed at the surface through hook or by crook. It's important to note that there's no evidence for an E-ring around any of the Uranian moons, Miranda or Ariel or any of them. And so I don't think there's hyperactive plume activity going on or anything dramatic like we see at Enceladus, but we could have gases kind of leaking out of their lithospheres. And that raises the question, right? If Ariel is an ocean world, where does it fit on the spectrum between, I'm bookending here with Ceres and Enceladus. I do think Ariel is or was an ocean world. I think it exhibits enough evidence both geologically and spectrally to support that. But whether it's active or whether it's dead is a better, I think, a more relevant question. I think there is sufficient evidence to suggest that it's at least at the Ceres level, where Ceres, of course, has these bright crater floor deposits, which are associated with carbonate salts, highly enriched in carbonate salts, as well as sodium chloride and other interesting components. Right, and so these carbonates, as well as CO and CO2, could have originated in Ariel's interior, as I suggested, perhaps from a soda ocean, so a saline ocean that happens to be enriched in CO2, which would suggest a fairly acidic pH for its interior. I'll leave that there. That's enough speculation. All right, so then switching to talk about UOP just a little bit, what does the future hold? What we want to do at Ariel and the other Uranian moons? There's a variety of science questions that were identified in the science traceability matrix for UOP. I'm just highlighting two of them here. Basically, what are the exogenic processes that are changing the surfaces of the Uranian moons, i.e. charged particle interactions, dust impacts primarily? And then what do their bulk compositions tell us about the formation and evolution of the system? So what's going on endogenically? What we really need is spatially resolved spectra and images. We don't have the spatially resolved spectra in any of the data sets that we have collected so far. And of course, we want to make measurements with a magnetometer and other parts of a field and particle suite in order to characterize moon magnetosphere interactions and look for evidence of induced fields. So I think I'm going to say more about spatially resolved reflectance spectra. Yeah. Okay, so what can that get us? And to an extent, it depends on the wavelength range. In the UV and Vis, it's a great wavelength range to look for evidence for radiation and also for evidence of exospheric constituents that could be enveloping Ariel and the other Uranian moons. And then the near infrared is really good for looking at endogenic tracers such as salts, as well as these ices, these volatile ices like CO and CO2 that I've been talking about. One of my favorite examples from a past NASA mission is Dawn at Ceres that got really close to Ocketer Crater and collected absolutely phenomenal spatially resolved spectroscopy of the bright crater floor deposits, again, showing that they are enriched in sodium carbonates and sodium chloride and other interesting salts that must have formed in Ceres interior and then made it to the surface one way or another. And so if we get spatially resolved data of Ariel, if we get close enough to characterize the spectral composite, the surface composition of the medial grooves versus the surrounding chasmata and then the surrounding terrain beyond that, I think that could get us some really tantalizing hints for what's happening on these moons and understand what's going on in Ariel's interior and how that material gets placed on the surface and then changed over time. Thank you for your attention.
All right. Thank you so much, Richard. This was a great overview of what we know about the spectroscopy of these moons and what we're still trying to find out. And I apologize, I totally forgot to do your bio introduction.
Oh.
And it's still feeling like a Monday. So I'm going to go ahead and do that right now while everyone think about your questions. Feel free to put them in the chat or raise your hand and I'll go ahead and call on you. So Dr. Richard Cartwright received his PhD in geology from the University of Tennessee, primarily working on ground and space-based telescope observations of the large moons of Uranus and other icy satellites. After graduating, he became a research scientist at the SETI Institute, working on a variety of projects related to telescope observations of icy moons and ocean worlds. He transitioned to a new position here at APL earlier this year. He's the PI of Hubble Space Telescope and James Webb Space Telescope programs that have collected reflectance spectra of the Uranian moons. And he has been observing these satellites from the ground for the past 12 years, primarily with NASA's IRTF on Mauna Kea. He has published spectral results and analyses on the Uranian moons in 8 papers over the past decade, revealing evidence for volatile transport and exposure of material that may have originated in subsurface oceans. So thank you, Richard. So go ahead and raise your hand if you have a question. I see we have a couple in the chat already. Jason Hofgartner asks, how volatile is H2O2 compared to CO2?
Yeah, that's a good question. And I don't have a good answer off the top of my head, but we do see it on relatively warm satellites like Europa and Ganymede, where it's being clearly it's being actively produced. I suspect it's not as volatile as CO2, but I would need to check the lab papers to confirm that.
Okay, we have another question in the chat about tidal heating. Who wants to ask it
Oh
live?
boy.
Feel free to go ahead.
And I'll
Oh,
feel
hi,
free
Richard. This is Burkhard Militzer from Berkeley. Great
hello.
talk. I really liked it. I learned a lot. I have a question about the beginning of it. When you talk about tidal heating and these resonances, you stated that they're not, it's easy to get into resonance. I just don't know how you get out of the resonance. Maybe you can educate me on this. And the second question is,
I can't educate you on that.
No?
I can't. I cannot. No, that's just what it states in the literature through the papers that I have on that slide and other papers too, that they used to be in these resonances and they have since fallen out. There may be somebody on this seminar who can speak more eloquently about orbital resonances than I can. I don't know if there is. I'm not volunteering anyone specifically.
Well, I will ask others. But the other question you said in passing at that moment, that even if you're not in a resonance, you still experience tidal heating. So for some reason, I'd like to know, do you know what this is about?
It's just a shared orbital resonance. The 5 moons may have some sort of overtone resonance of some sort. So even if only 2 of them are in resonance, the other 3 may still experience heating as a consequence. And that's summarized in Chuk et al. 2020, this paper right here, if you're looking at my screen.
I will look at that. So thank you.
Check it out. Yeah, it's really interesting modeling result that they have.
Fine. Thank you so much.
Yeah. Sorry, I can't be more help with tidal heating and orbital resonances. I'm a spectroscopist.
I thought I saw another hand from Mark, but it doesn't look like that hand is up anymore. I see Francis Nimmo posted something in the chat related to resonances. Feel free
good.
if you want.
I can't see the chat, but
Francis, if you're online and you'd like to.
Yeah, this was just answering Burkhart. Basically, the resonances overlap with each other, and so you end up in this sort of chaotic system where you could just drop out of a resonance automatically. There's a good paper by Dermot et al. 1988 that explains it. So that's the place to go look.
Okay. Okay. Since nobody else has a question for, I'm asking you a second one. You mentioned phonons, right? Molecules condense into a solid, and that's down your alley. And so all of a sudden you're detecting phonon bands. That basically you say it's not amorphous carbon CO2, it's actually crystalline stuff. That's basically, that sounds like you can tell how quickly it condenses, and you can relate this to lab experiments. Because otherwise you shouldn't see phonons, I think. Isn't there something that should be done?
That's a good question. I don't know if Will Grundy, I saw his name on here, I'm throwing him under the bus. If he could give a better question or a better answer in terms of the condensation rate of CO2 and what that and how that might relate to phonons. He might not have a mic. So I can't specifically talk to that in terms of its condensation rate, but I do, as I said, I do think it means that there is a lot of CO2. We see, for example, I didn't show it. I might have put it as a backup slide. Oh, I did. Perfect. You see this plot?
Yeah.
So this is showing the 2 aerial spectra colored here versus 3 TNOs, which were observed with JWST, same instruments. And so we see strong scattering peaks and some TNOs for CO2. and then we don't see it for all the different sorts of examples. So 1, 2, and 3 are representative of different types, different classes of TNOs. If you look at 4.9 microns, maybe this number 3 shows some speculative evidence for this 4.9 feature, but the other two don't. And so I think this is indicative of needing a thick layer of CO2 in order to show this biphonon plus phonon combination mode.
So from a condensed matter point of view, is one is amorphous and the other isn't. There is a minimum thickness, otherwise you wouldn't see it. But I don't think you can tell the difference between half a millimeter of CO2 and a meter of CO2. But you can tell it's amorphous or not.
I think I understood. I think I understand what you're trying to say. Yes, we can tell that it's crystalline for sure. It doesn't show features that are associated with amorphous CO2, at least none that are dominant. And I think, and your other point, I think, is correct. Sure, we can say there is a centimeter of CO2, but it could be more than that. That's absolutely true. That's just the limit of the photon penetration depth approach. It's certainly, it's not penetrating the entire CO2 layer. It's just penetrating a centimeter at most.
Fine, thank you.
All right. We do have a comment from Shoshana Cole, who says you could also get a crystalline structure through post-depositional annealing, for example, if the deposit gets heated. We do have another question from Hans. Would we expect clouds or perhaps tori of CO or CO2 in the magnetosphere? That's
a very exciting question. I do wonder about that, based on the fact, I mean, Enceladus, it's such a hyperactive moon. It's hard. I don't want to make too many ties to Enceladus, but we certainly see a torus of water vapor around Enceladus. And there could be something similar with CO2, maybe not as pronounced, not as dense as what we see at Enceladus, but I wouldn't be surprised if we have something like that with CO2. And we wouldn't be able to see that, I don't think, in the JWST data. We would need to go to the system in order to characterize the torus, if it exists.
Okay. So feel free to put some more questions in the chat or raise your hand. I have a question.
Yeah.
So you've done so much observing of these moons with Hubble and with James Webb. In preparation for UOP, do you think there are specific questions that can still be answered with telescopic data?
Oh, yeah.
In preparation for this mission?
Absolutely. Yeah, absolutely. And this is something that we're continuing to work on, is the seasonal migration hypothesis is still, it's been tested, but I would still consider it to be quite a ways away from being confirmed. And so something that we're continuing to work on is observing the Uranian moons every year as the subsolar point migrates further and further north. And at some point, I will analyze those data and be able to give an update on, do we still see a reduction in the amount of CO2 at their north poles versus what we have collected 10, 20 years ago at lower subobserver latitudes. So that's a big one. There's a similar case to be made for the distribution of dust. So the distribution of red materials, what we can detect, if it is primarily from a regular satellite dust, we might expect that to concentrate at low latitudes. I think that's what the models would mostly support. And in that scenario, we might expect to find less red material at the pole versus at low latitudes. So there's some work to be done there. There's other things as well, but those are some easy ones.
Yeah, thank you. Okay. Well, keep thinking about questions. If you have them, put them in the chat. I'm going to take this screen sharing here, and I'm going to share our community news slide. Oh, please current share.
You mean to stop sharing?
I got it. Okay. So, and I'll go ahead and put these in the chat. So every month we try to give an update on relevant meetings, other things that are, will that go into the chat? It might not let me put it into the chat. Oh no. No, it's not going to let me put it in the chat. Well, if you're interested in these, maybe take a screenshot and look these up yourself. So we like to give an overview of some seminars that are coming up, meetings that are relevant to the community. So next seminar we have is in November on the 12th. Dr. Marisa Parisi from JPL will be giving a talk, so tune in for that. DPS registration closes on September 12th. So if you're planning on attending, you might want to get your registration in pretty soon. We have a couple of seminars related to mental health and DEIA in the community. There's a professional development seminar on mental health and planetary science. And the Advancing IDEA conference in October, that's going to be a fully virtual meeting if you're interested in that. And I don't think they're collecting registration fees, so it's pretty accessible. There's a couple of open positions, a department chair position for the Department of Physics and Applied Physics at the University of Massachusetts, Lowell, an assistant professor position in the Department of Astronomy at Berkeley. Save the date for the next OPAG meeting, which is going to be in November, and I believe that's also fully virtual. And then there is a list, community list for people actively looking for master's and PhD students, which is a great resource, especially for those who are looking for master's or PhD programs, looking to get into some of those. Let's see, we have a little bit more in the chat. Okay, yes, Shoshana is confirming that the Advancing IDEA conference is free and completely virtual. So please do check that out. That's going to be a great resource for the community. So with that, I don't see any more questions in the chat or any hands raised. So thank you so much, Richard, for this wonderful talk. And everyone have a great rest of your day. Take care.